There he is.
Hello. You see my desktop?
Yes.
Yes.
Okay. Everything seem okay?
Mm-hmm.
Okay, so let's see. I'm still trying to get the videos up, the videos from the course that we meet. I'm going to hopefully get them up either on YouTube or Blackboard this evening. So I'm going to give that a try after class. So I'm hoping to have, I'll put a link. If I get them up on either one, I'll put a link to them. Well, if they're on Blackboard, I don't know if I can put a link to them here. If they're on Blackboard, I'll have to have like an announcement on Blackboard. I'm going to try to get them up on YouTube. If I get them on YouTube, I'll just put a link to them here on the course website. Okay. If they're on Blackboard, I probably can't link to them from the course website, so they'll probably have to link to them from within Blackboard. Okay. So I'll figure out which one works. And let's see. If you have questions, just send me an email or whatever. Today we're going to keep looking at the fork join. Spend another day just look at some more examples of fork join. So what I'm doing is I'm actually following this handout here, this Introduction to Shared Memory, Parallelism, and Concurrency. Okay, the code we were looking at on Monday came from there, and here's what that paper looks like. Okay, like it's this paper here. Okay, and if you go to page, I think it was 17, the stuff on fork join. So he starts here at section, well, actually, he does it, this is actually pretty well written. He does a good job of motivating, starting here, he motivates fork join. So, for example, section 3.1, that's where, okay, if you download the code from this fork join folder here, okay, in the code folder, okay, I've got section 3.1 Java, section 3.2 Java, section 3.3, and section 3.4, 4A, and 4B Java. Those are the code from, see, section 3.1. The example from here, so if you want to read here and you want to follow the code, it's over here. Now, one slightly not good thing about this thing, what he did, he has code in here, but it doesn't run. Yeah, it's too sketchy. So I took the code from here and I just added a little bit of more boilerplate to it and turned it into code that will actually compile and run. So like this is not a runnable program here. But I took this and added a little bit of boilerplate to it and turned it into this runnable program over here. Same with section 3.2. Okay. Now, this is the code that we were talking about the other day. If you have a big array, the easiest thing you could do is say, I have 4 cores in a big array, so why don't I just chop the array into 4 pieces? That's this example here. This chops the big array into 4 pieces, okay? And then that's what this code here actually then does. But it actually will work. This one will compile and run, okay? It creates 4 threads and chops the array into 4 pieces, okay? And this compiles and runs. If you, okay, you notice the parallel solution wasn't much faster than the sequential solution. I'm still not quite getting it why I'm not getting more speed up. Yeah, this is, this is a little bit close to twice as fast. Um, in theory, it should be 4 times as fast because I'm cutting the work into 4 equal sized pieces. Um, I could try doing a bigger problem size. Notice that, if anything, it didn't get any better at all. Okay. It didn't get any. See, notice here, the parallel is almost twice as fast as the sequential. Here, the parallel is only a little bit faster than the sequential. Okay. Now, it might be because this machine is overloaded already. I don't know. The machine is kind of heavy. I think maybe because we're doing zoom on this thing, that maybe this machine is just kind of, you notice that it's just idling at almost 30% CPU utilization.
What are you running in the background?
Pardon me?
What are you running in the background?
Nothing. Zoom. Yeah, I know. I've been sitting here wondering, like, what's going. I've been wondering the same thing. Other than Chrome and Zoom, nothing. See, Zoom's using up a little bit of time. Yeah, I don't really understand what's going on in this machine.
There's not enough numbers there to make up 30%
Yeah,
on
and there are
6 cores.
Yeah, I know. So, I mean, Windows might be doing a bunch of stuff in the background that it's not
Oh,
even.
no, it's Zoom.
Hmm?
It's Zoom.
How do you know?
Zoom's coming up at like 20% sometimes. Yeah. But just not in your details view. It's weird.
But over here, maybe?
In your processes list.
Oh, over here.
Yeah, sort by CPU usage.
I almost never look at this window. Yeah, that's funny.
Yeah, no, that makes up 30% right there.
Yeah, but why is this window showing different than this? I never used this window. This window wasn't part of Task Manager in the old version. Like Windows 7 and before, this window didn't exist. The details window was the main one. But they're not reporting the same numbers.
No, not even close.
Yes. Well, so I'm not, wow. What the heck is this? Why? Yeah, because this makes more sense. Zoom is chewing through a lot of CPU time. Okay. Whether that's affecting the parallel processing, it's still not. That still leaves a lot of CPUs, left over.
Can you give a copy of your sequential code?
Pardon me?
Can you give a copy of your sequential code?
I'm not sure what you mean.
The code that adds the entire array in sequence.
Yeah.
You didn't put that to the
Yes, I did.
You didn't? Or you did?
I did.
Hmm.
Yeah, I put it up there last night. See, it's right here.
Oh, okay.
Now,
3.1. Okay.
check it, download it again. Because I had trouble with my other course. The web server kept serving a stale version of one of my files. And I got really stuck. I couldn't figure out some reason, unless maybe this is happening here too. In one of my other classes, the web server kept serving a stale version of the code. Because last night I put the serial code up there. So you should be able to download. I can do it even here. Let's see. If I download fork join, show all, show in folder. Let's see if it looks like it's there. Wow. The same thing's happening. The web server is serving a stale version of the file. Somewhere that file's been cached, and the web server is insisting on serving the stale version. See, so the serial code's not, the version I just downloaded, the serial version's not in it. Okay, that's two classes now. The web server is serving a stale version of the zip file. The other one, I deleted the version, I deleted the file from the server, re-uploaded it, and it still kept serving a stale version of it. It's been cached somewhere. I have no idea how to figure out who's caching it. Do you guys get, are you guys seeing any of the parallel code or the serial code?
I didn't.
Yeah, so yeah, there's the, okay, here's the two versions. Okay, there's the old version, there's the new version. I put that new version up there like at least a day ago, but the server's still serving up this old version, missing the, here's the little serial part, the part that just does the calculation in serial. That's, you know, that's the little sanity check to make sure that you're really getting the right answer from all the parallel code. But that's up, yeah. This version is up there on the server, but the server is refusing to serve it. I'll try to figure out what's going on with that too. Okay. But, okay, so multiple little problems to sort out, okay? And then there's just the issue of like, why is the parallel code not really running, you know, any, again, you know, if I run this, you know, even though I'm using 4 cores, boy, look at, they're almost a tie. You know, the sequential code was negligibly faster than the parallel code, even though the parallel code ran on 4 cores, okay? Yeah. And there's no hint over here. Yeah, you can't even see what's going on over here. This is one of the things that makes parallel programming kind of a, it's kind of well known that when you're writing parallel programs, if you really want to see what's going on, you have to get on a machine that doesn't have a lot of junk on it like this. Like this is just not a good machine to be doing this on. These are experiments that should be done up on a server somewhere. You know, it's way better to do this by uploading the code to a server somewhere, and like Purdue West Lafayette's servers, and running the code on a server that's going to be cleaned. It's not going to have all kinds of background processes running on it. So like now, if you see, it's, the machine's quieted down a little bit. If I run this, I don't know if we can see. See, there's spikes all over the place. We don't even really know where that code went. It was somehow, see those spikes there? That was our 4 cores, but it was all over the place. Okay. All right. So the code is written. We can see what parallel code looks like, but we're not getting the benefit of parallel code, which is in a way a good lesson. Parallel programming is strangely hard. Okay, everything you think should be happening kind of doesn't happen the way you think it should happen. Okay, so this version here just chops the array into 4 pieces and runs just runs each piece on one core. Okay, then the next version that the author wrote, okay, from the next section of his book, okay, so that was section 3.1. Okay, then section 3.2, that's when he pointed out that you might have 10 cores, you may have 12 cores. So why the magic number 4? Okay, now the obvious answer in this section, which is what he didn't do, would be to ask how many cores there are and cut the array into that many pieces. He doesn't do that example. But he also does point out that that's not a great idea either, because that's what we talked about the other day. That's the load balancing problem. If you have 10 cores, so you cut your array into 10 pieces, that doesn't mean that there's 10 equal size amounts of work. Just because you cut the array into 10 pieces of equal size doesn't mean you've cut it into 10 equal size chunks of work. So you could have some cores finishing work before other cores, so then you have idle cores. Okay, so that's not what he thinks is a good idea. So this is where he introduces the idea that you should cut it up into lots of little pieces. Okay. Okay. So then there is the idea of he explains why not to use 1 thread per processor. So he explains what you don't want to do. You don't want to do 1 thread per processor. Okay. So here, this is what the code looks like. You just chop the array into a lot of pieces. Let's see, let's go down here. Where's the array being chopped up? Oh, I'm sorry. Okay. I've lost. Okay. Oh, I'm sorry. This part lets you choose how many pieces to cut it up into. There's the parameter that so this one just lets you choose how many pieces to cut it up into. So right now it's set up to cut it up into 2 pieces. So that array is just cut into 2. And actually here it was cut into 4. Here it's cut into only 2, but you can change that parameter and cut it into as many pieces as you want. But it won't end up making things very fast, okay, as he points out in section 3.2. Okay, so then the more interesting thing is what he says you should do. If it isn't, oh, let's chop it into how many ever cores we have, that's not a good idea. Why not to do that? Okay, why not just have 1 thread per processor? Okay, so then you start getting into, you really want a lot of little threads. This is the key idea, divide and conquer. This is where the recursion comes in. You'd really like to have lots of threads, but you don't really know how many to do. Like, should there be 100 threads? Should there be 1,000 threads? Okay, so the idea here is, now this is not using fork join. This is still leading up to the idea of fork join. Here, essentially, this is really just merge sort. This is written very much like merge sort. You're going to just take the array, cut it in half, send it each half. We drew these pictures the other day, and at least I tried to draw them the other day in class. Take a big array, cut it into 2 pieces. Then, if it's not small enough yet, cut it into 2 pieces again. Once it gets small enough, you solve the problem just like that. Once these arrays are small enough, you just solve them sequentially and then return the answer to the parent, then return the answers to the parent, return the answers to the parent. Okay, and that's done during recursion. This function call recurses on this half and recurses on that half. When it recurses on this half, it will see it's too big, and it'll recurse on this half and recurse on this half. Okay, so that's the code in this file 3.3. Okay, this takes the array and cuts it into two halves and creates a thread for each half. So it creates a thread for the left half, a thread for the right half, okay? And then it starts the left half, starts the right half. Over here, that would be start up the left half, start up the right half, then wait for them to be done. So then this one waits till that one is returned and till that one is returned. While he's waiting, this one's dividing himself up into pieces. This one's dividing himself up into pieces, but he's just waiting. So he just waits there. So he starts up the two threads, waits, okay? Then when they're done, he can get the answer out of each of them, okay? Right? Now, that's one way to do this. And then there's actually a second way to do it. Instead of doing it that way, you can comment out this piece. You could also do it this other way. Okay, this other way is the more clever way. You have this thread up here, and he creates a thread to do this half, and he creates a thread to do this half, and then he just blocks. So you've created a thread that did almost no work. All that this guy created this thread, and all he does is create two more threads, and then he blocks. It would be wiser for this thread to create a thread to do the right half, and then this thread it goes and does the left half. So we mentioned this the other day. The clever thing to do is not have this thread create two threads, have this thread create one thread for the right half and launch it, but then this thread just jumps in and it does the left half itself. That's this code here. Okay, you create the two threads. Now remember, this is where Java lingo gets kind of broken. Here I created thread objects, but remember, thread objects aren't threads, and threads aren't objects. So when I create these thread objects, I'm just creating these bookkeeping entities. This actually creates the thread. The start function creates the thread. So you don't actually get a thread running down here until you call start. Okay. Now, I create two thread objects and I start this one. If I just want to jump into this one, I call its run method. Because remember, a thread object holds a runnable object. The runnable object is actually the code that you run the thread in. So on the right, actually here on what I started the left half and I'm jumping into the right half. Okay. Notice how I use the words over here. This is an asynchronous thread. This is a synchronous function call. When line 45 returns, this guy's done all his calculation. So when the right guy returns, I fork a thread over here, but then I jump down into here and do all these calculations. So I'm actually doing, okay, this left.start is starting a thread down here. Right.run is jumping down into here and doing this calculation. When it returns, there's an answer. The right half answer is done. So I only need to join the left half because I asynchronously launched the left half, which means I don't really know when it's going to complete until I join it. But I synchronously ran the right half. I called that thing and I called it, and now when it returns, I get the answer. So this is real clever. asynchronously start the left half, synchronously run the right half. Oh, what happens if you goof up and you do, here's a real common mistake if you don't pay attention real carefully. What does that do? It's a dumb little mistake, and if you make this mistake in your parallel code, you lose all your parallelism. Why? You're up here, and then you do what? Line 44 does the parents up here, and then
Does it
line
just
40.
block
Slow
on the
down
run until it's done?
Pardon me?
Won't it slow down, Professor, if we do the write dot run synchronous call and then call an asynchronous thread?
Say it again.
If we interchange these two executions, then won't it slow down the response?
Doesn't slow down the left one, it's worse. It's worse than
No,
slowing.
actually in the end response.
Pardon me?
If we do write dot run, then the write portion will be done in synchronous manner. So we have to wait till it is completed, right?
Yes. And then you do what?
Yeah, and then we do left. So won't it slow down the response?
No, it doesn't slow them down. It serializes them. It does all of the work in right first, then it does the work in left. So it completely eliminates the parallelism.
So you only get one thread running at a time.
Yes, exactly. That's a good way to put it. There only ends up being one thread running at a time.
So
Because
even if your machine has, let's say you're on some sort of monstrous machine with 128 threads, you're only using one of them.
yeah, because you jump into the right. See, before you notice you can't launch left until you've finished running right. So you go down here and you do all the work on right, and then you can go back up here and launch that thread. But then when you launch that thread, you wait for him to finish. So you've ended up serializing the code. So this is really touchy stuff. You have to be very careful that you don't, that you have to write it like that. Yeah, see, that launches the left. So now this is running on a CPU. Then you call the right. So this is running on one CPU while you're doing this one synchronously. So you launch the left and then you run the right. But if you do it the other way around, it's just, it looks like it's just, you know, if you're not careful, if you treat this code as if it was serial code, yeah, but now you've completely destroyed the parallelism, because now you're going to run right till completion, and then you launch left. So you've serialized the two branches. So then it's no different than if you just did run, run. See, it would just be now it's exactly the same as if you did run, run, because you're going to run everything down here, then run everything over here. So the start actually does you no good at this point. Okay. So this is a tricky little thing. And this is one reason why parallel code is kind of tricky. Simple little changes in your code make monstrously different changes to performance. So it's got to be fork one half, run the other half, and it has to be in that order. Fork one half, doesn't matter if it's left or right, but you fork a thread in one half, get it started. Then when this thread is started, then you can synchronously go down into this one. When this one's done, you go up here and wait to see if this one's done. So you only have to join the other one. Okay. Now, so this is going to do, oh, and then at some point, you know, you get to a small job and you do it sequentially. So you probably don't want to get your small job to be an array of size 2. You probably want your small job here. We use a cutoff of, was the sequential cutoff was somewhere around 1,000. Okay, that's the one the author used in his book. That when the array is about 1,000 items big, then you just switch to your sequential answer. Okay, and that's, see, that was this if part here. See, we were looking at the else part. That's the parallel part. That's the part that says split it up. But if your size is small enough, just do a for loop. See, when you finally get to a thing that's small enough, you don't fork two threads. You just go ahead and solve the problem. Okay. Now, this creates a lot of threads. Okay. This creates a lot of threads, and this looks a lot like fork join, but this is not quite what Java calls fork join. And because these are threads, not tasks. And one of our big emphasis is that we really want to replace threads with tasks. Now, right now, if I run this one, I'm not surprised that the parallel version doesn't do very well. Let's see how it does. Wow, it's really slow. Notice that my memory usage has gone up a lot, and my CPU usage is going up a lot, because I'm not surprised. This is actually bad parallelism, okay? I have an array of 100 million, okay? I stop creating threads when I get down to 1,000, okay? How many threads do I have? You can kind of see it. I'm going to need 100,000 threads, because I'm going to need 100,000 things of size 1,000. See, a problem size is 100 million, so that's 100,000 1,000 size arrays. Let's see, can we see it? Let's see how many threads we've got so far. So this is our Java process. We are kind of ridiculous, right? See what we got so far? See why we're bogged down? Operating systems don't really like to create thousands upon thousands upon thousands of threads. They choke on it. So, I'm doing parallel programming, but so far I'm up to, the numbers are going down. That may be, maybe the threads are starting to complete now. The number of threads is going down, 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 so that we're there. See, the answer came back. Okay, so it built up a huge number of threads. And so if you think about this picture, the number of threads built up to some huge number of threads down here. Then the threads started joining back up. Okay, but it was a ridiculously, notice that the parallel time was 1,000 times slower than the sequential time. Okay, so what's really kind of neat about this is what we just did is that the core idea of fork join, but we did it the wrong way. Okay, we created lots of little jobs, but we created them as threads. We're really not supposed to create them as threads. We're supposed to create them as tasks and put them in a task pool that a small number of threads can pull jobs out of. That's what we talked about the other day. You don't really want to have all this forking going on, creating honest-to-God threads. Okay. And one of the things that's confusing about this, even this handout that I haven't you read that I said is really well written, even this handout, there's people really blur the idea of creating a thread and creating a task. What we just did created thousands of threads, which meant that we actually told the operating system to create a thread data structure for every one of these little tasks down here. The operating system created a thread data structure, okay? Because now it isn't creating the thread objects that's causing a problem. We were not bothered by having created thousands of objects. Java is actually really good at creating thousands and thousands of objects. You can create objects by the hundreds of thousands, and the Java virtual machine hardly skips a beat. But starting threads is nuts. Okay. Luckily we did that in this case, not this case. Remember, we didn't run this one. Why is it lucky that we ran this one, not this one? What was better than about running this one versus running this one?
The bottom of we are starting the left half and we are running the right half right away. But in the top part we are starting both and it takes time. Then we are joining them.
Yeah. So what's bad? What would have been? What would have we seen if we did this one?
It takes more time than the bottom of.
Pardon me?
It takes more time than the bottom of.
Why?
Because we are running the right half on in the bottom of, and we are starting the right half in the top one. In the 36th line we are starting it. In the 45th line we are running it.
Remember when we ran this, we saw like 20,000 threads, right?
Yes.
How many would we have seen here?
40,000.
40,000, twice as many. Yeah, down here we saw half as many threads as we would have seen up here. And that would have just even choked it even more. Okay, and you can do this at home. You can, notice that it didn't crash the machine. It's if you create 40, 50,000 threads, it's just kind of slow. But this one is going to create even more threads than this one did. Okay, now it's not creating the thread objects that's actually the problem. The Java virtual machine can create thread objects like crazy. It's the operating system creating actual operating system threads that's going to kill you. Okay, so it's the actual starting of an operating system thread, not the creation of a thread object that's a problem. Okay, what we want to do is, instead of having these objects be thread objects, we're going to make them essentially just runnable objects. Just make them tasks, and then we won't start threads in them. We'll just put them in a thread pool. Okay, so we're going to create the thousands upon thousands upon thousands of tasks. That's not a problem, but we'll want to put them in a thread pool and then not do this. Okay. Okay, so then that's the next version, 3.4. Okay. Okay, and if you go over here, see, that's when, okay, here's his, now again, his code won't compile and run. Okay, but like over here, I added just enough boilerplate to his code here to make his code here actually executable code. Okay, so this is the part that does, see, left start, right start, left join, right join. So this is creating the thousands upon thousands of threads. Okay. The next thing is actual to use fork join itself. Same idea, but now switch to actual fork join. If you look at this code and you look at this code, there's not a whole lot different. Okay, look, actually, see, if I switch between them, there's not massive amounts of difference, okay? Okay. Instead of having some threads, I'm going to create some array objects, okay? These guys are, well, see here, some threads extended thread. Some array extends recursive action. That's one of the key differences. These are the tasks. They're really not going to be threads. They're just going to be tasks. So I'm switching from creating real threads, I'm switching to creating tasks. Now the code in the thread and the code in the task are the same code, except for one little difference. Okay. So this is the code in a thread. Let me get rid of the, let me just switch to the one version of it. Okay. Look at the difference. Can you kind of see that there's really not that much difference going on? Okay. Okay. This is a thread object. This is a recursive action object. A thread object has a run method. A recursive action object has a compute method. The compute method looks to see if he's small, just like the run method. See, they're doing, in the case of small, they do exactly the same thing. If I'm small, I just do my own work. Okay. The key is what happens when they're big. Okay. So now look at, if they're, first of all, if they're big, they start off by doing essentially the same thing. Create a left and right half of myself. This one creates a left half thread and a right half thread. This one creates a left half recursive action and a right half recursive action. This guy starts the left thread and jumps into the right thread. This one forks the left thread, which really means, we talked about this the other day, what does that mean? What does it mean to fork a task? What do you do when you fork? We know what it means to.
You split it into smaller tasks.
No, not, no, no. What is it? No, that will be, that's what's going to happen when you, it will, all, you know, everything is going to be subdividing itself. What does this do? This guy's a thread object. And you call the start method on a thread object. What does that do?
Creates the thread.
Creates a thread and launches it on you know, and gives it to the operating system scheduler. Okay. When you start a thread object, you create a thread and you give it to the scheduler. What does it mean to take left and fork him? Give you a hint. It does not create a thread.
It makes another recursive action object.
No, we already did that up here. Here's where we created the recursive action object. Right here. There's the objects. Just like here,
Oh.
There's the threads. So the objects are already created. Here we start that thread as an actual thread. So here we created the thread object. Here we create the thread in the, notice how confusing it is. Here we create the thread object. Here we create the operating system thread.
Mm-hmm.
Okay. Now here we create the recursive action object. What does this do?
Adds it to the queue to be run eventually.
Yes, it only puts it at the end of the queue. It puts it at the end of the work queue. So it's like the, you know, writing a little task on a slip of paper and putting it in the task jar for somebody to go get it later on. It doesn't actually start any work. That's a huge difference than left.start. Okay, there's the big difference. In this model, we actually created a thread and started an operating system thread. In this model, we created a recursive action object and put it in the cookie jar for somebody to get out later and do the work that's written on that little task. Okay, this does not create a thread. It puts it, so the fork method actually just says, let me take this object and put him in a queue. That's all it does. Notice it doesn't fork anything. The terminology is very confusing, but meant to be evocative. You know, you're supposed to think of it as kind of like starting a thread. But you're not starting a thread, because we just saw over here that starting threads is a heavyweight operation. If you start thousands of threads, you hammer the operating system. So what we're going to do is we're just going to say, oh, put this object in the work queue jar for somebody to get later on. Now, and then over here, we jumped into the right guy, and here we do the exact same thing. We call compute directly on the right guy. So we just, the thread we're running in right now, see, we're running in a thread here. So that thread that we're running in, it just puts this thing in the cookie jar, and then it goes and does the compute here. So that thread jumps into here, just like over here, this thread, it launches this independent thread on the left, and then this thread jumps right into the right. This thread here jumps into the right half. Remember, in our picture here, we could think of it as this thread that's doing this work launches this thread, but this thread goes down into here. In this way of thinking, this thread puts this guy in the cookie jar and then jumps down into here. When it's down into here, this thread's moved into here, it'll create this right half, put that in the cookie jar, and jump down into here. So that thread, so if you think about the thread that's executing this, will execute this, will execute this, will execute something down here, and it'll keep putting this in the cookie jar, this in the cookie jar, something down here in the cookie jar. These will be gotten out of the thread, out of the work queue later by some other thread. Some other thread will eventually pull this one out of the work queue, and then when some thread pulls this out of the work queue, it'll cut it in half, put this half in the work queue, jump down into this half. So whatever thread pulls this out of the work queue, he'll put this half back in the work queue, and he'll jump down into here. Then he'll cut this in half, put a half into the work queue, jump down into here. So threads kind of go down like this while they put things on the right into the work queue. Okay? So there's it's actually very, you have to really think hard to see how this code, part of the lesson here is that people think that programming is easy. You just learn to read the code line by line. Okay. What we're seeing now is that programming is really actually hard, because just because you read code line by line, what do you need to know? You need to know all the details of what every line does. Okay, so like this code and this code superficially look like the exact same lines. They even have very similar sounding names. Okay, it looks like they're doing the exact same thing, but the meaning of that line is profoundly different than the meaning of that line. Profoundly different. Okay, so that creates a heavyweight operating system thread that puts an object in a queue. That's all. It just inserts. I mean, it might have been better if they actually said left.insert. You kind of wonder, like, okay, why didn't they call that, instead of calling it fork, they could have just said insert in work queue, because that's exactly what it does. Fork doesn't fork. Now, the trouble with fork, like if you're a Unix programmer, fork means create a new process. So the word fork is a very overloaded term. In a lot of environments, fork literally means create a whole new work environment. In Linux, it means create a new process. In some libraries, it means create a new thread. Here, fork means put something in a queue. That's all. Okay, so they actually probably should have called it insert into work queue, because that's all it does. And then it wouldn't have looked so much like start. Start, fork, okay? You think, oh, they're synonyms, but they're not anything close to synonyms. They're not even close to synonyms. Okay? Okay. Oh, I actually made a little mistake here. See, I said the word asynchronous there? That's not. Okay.
Isn't it though?
No, technically it is not. Okay, because see, what does this do? This is actually, well, okay, it's ambiguous, because what does that function do? It returns to me immediately.
Mm-hmm.
So in a sense, it's just like it's a void function that I called synchronously, and all it did is, like, if you call push on a stack, do you think of that as asynchronous?
I mean,
You don't, do you? But what did fork really do?
fork really put something to do in a queue.
Right, it did a push.
Mm-hmm.
Right. So is it synchronous or asynchronous?
I would call that asynchronous.
But would you call pushing an item into a stack asynchronous?
No, that's synchronous, because
Right, but that's all this guy did. He pushed
putting
something
the
into a
item
stack.
on the queue is the main
Well, yeah,
goal
see,
of
that's
a push.
right. So the goal of this is asynchronously to put some work to be done later
Mhm.
on. But it still is a synchronous operation. It's just push onto a stack. So it's very, see, my point is that the semantics of this little line of code is really subtle. You're doing nothing more than pushing an item into a stack. Okay, that's very synchronous. But the item represents work to be done later that's going to be pulled out of the stack by some worker thread later on. That's asynchronous. So the work is going to be done later on. So are we emphasizing the push, or are we emphasizing the amount of work to be done later on? Usually we emphasize the work to be done. But notice, so I wrote asynchronous, put left item in the work queue. So maybe I can write it a little better. This is a synchronous operation. Put an item in the work queue. The item in your work queue represents an asynchronous task to be done later on. Okay, so you're synchronously putting into the work queue something that represents an asynchronous amount of work to do later on. That's pretty subtle. Okay, that's a pretty, and that's very different than what this guy meant. Okay, now this line here means almost exactly the same thing as this line here. They mean exactly the same thing. They mean go jump into the left half and start doing the work. Jump into the left half and start doing the work, which means first, well, now if the left half is small enough, you'll actually do the work and return. If the left half is big, when you jump into the left half, you'll cut it into two pieces. You'll create a task for the right half, and then you'll jump into the left half. Okay, so the right run here and the right compute here really do mean almost exactly the same thing. Okay, now since we forked this guy and he's asynchronous, this is where the asynchronous part comes into play. You have to wait for him to finish. So that emphasizes the asynchronous aspect of this guy. You're saying that you want this work to be done later on. So since it's going to be done later on, you have to wait for it to be done. When line 36 completes, all the work on the right has been completed, but you don't know when the work on the left is completed. Now over here, notice that the left join, this is just a quirk of Java. When you join a thread, you have to catch an exception. When you join a task, there's no exception to catch. Okay, so this line of code here means exactly the same thing as that line of code there. But for some reason, the Java designers decided that when you join a thread, you have to catch an interrupted exception. When you join a task, there is no exception to worry about. Okay, but the actual joining here means exactly the same thing as the actual joining here. So this little piece of semantics and this little piece of semantics are the same thing. This little piece of semantics and this little piece of semantics here are the exact same thing. The big, big, big difference is that one versus that one. Those two are the really important differences. Start versus fork. Start, create a heavyweight operating system thread. Fork, put this object in a queue for somebody else to get to later on. Okay? So then in the fork join, in this way, there's only going to be a small number of threads. For example, in this picture here, this picture shows 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This one shows 19 tasks. Okay? That was the initial task. It got split into 2 tasks. It got split into 2. Each got split. Now, in version 3, this is 19 threads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, this is 19 operating system threads. Okay. Over here, we don't know how many threads there are in this picture. If we have a 2-core machine, there's going to be only 2 threads. If we have a 4-core machine, there's going to be 4 threads. If we have a 6-core machine, there's going to be 6 threads in this picture. Remember, and what it does is, suppose there's a 2-core machine. Let's think of it as let's try to imagine if we can step through this with 2 cores. This task is the starting off. So only 1 core can run that task. So that core, so 1 core is running that task. Then that core creates a thread and puts, that core creates a task and puts that task in his work queue. And then that core goes down here. Okay, so he put a task in his work queue, and then he goes down here to work. What does the other core do? We start off with 1 task, so we have 1 thread. So that means the other core has got nothing to do. This 1 thread puts a task in his work queue, then he goes over here. What's the little magic step right now?
The other thread grabs what he put in the work queue.
And we call that what?
Work stealing?
Work stealing, yeah. The other thread, which had no job, he steals that one. So thread 2 steals that thread there, steals that task there. So now thread 1 has got an empty work queue, and thread 2's got this guy in his work queue. Okay, now thread 1, he's over here. He splits this thing up into 2, and he puts this guy in his work queue. And then he goes jump down into here. Okay, then thread 1 cuts this guy into 2 pieces. He puts this guy in his work queue ahead of that guy. Now this guy's just sitting in his work queue because he's working over here. This guy's sitting in his work queue. Now this guy and this guy are in his work queue. And he gets down here and he does this one. Meanwhile, thread 2 now says, oh, I got something to do now. I'm going to split this in 2. And I'm going to put this right half in my work queue, and I go into here. So now thread 2 has got him in his work queue, and he jumps into here. He cuts this into 2 and puts this one in his work queue behind this one, and he jumps into here. And then he does this. Maybe this is small enough that he finishes it. So when he finishes it, he's got nothing to do because he's not going to fork down here. So now he goes to his work queue, and he goes to the end of his work queue and finds him. And he does him. Then when he's done with him, he's done working. There's no more jobs to create. So he goes and looks in his work queue and finds him at the end of his work queue. So then he splits him into 2, puts him in his work queue, and goes into him. Meanwhile, this guy was down here. He finished this job, got this job out of his work queue, finished him. There was nothing to do down here. And then he goes and grabs this guy out of his work queue. When he grabs this guy out of his work queue, he cuts into 2, puts him in his work queue, and grabs him out, and then jumps into here and does him. Notice that we're talking about how 2 threads traverse this tree together. It's a very weird strategy, but there's two threads traversing this tree in a weird little dance of putting things into their work queues, and putting, like, he'll put him into a work queue, go do this. Put him in the work queue, go do this. Since this guy's in the work queue, none of this shows up yet. None of this shows up yet until eventually this guy finishes these jobs and then goes into his work queue and grabs him out. Then he starts saying, oh, now I'm working on him, I'll cut him into two, put this guy in the work queue, go put this one. Okay. Now, what if there were four? Now you can start all over again. Suppose this guy, suppose we go back to the top. Suppose we have 4 threads. Suppose we had 4 threads. So thread 0 starts off with him. Thread 0 takes this guy, puts him in his work queue, and jumps down into here. Okay. As soon as thread 0 puts this guy in his work queue, thread 1 says, now I got something to steal. So thread 1 steals this out of his work queue, out of thread 0's work queue. Okay. Thread 0 is down here now. Thread 0 cuts this into half and puts this guy in his thread pool, in his work queue. As soon as thread 0 puts this guy in his work queue, what do you think happens?
Thread 2 steals it.
Pardon me?
Thread 2 steals it.
Yeah, thread 2 will steal it. At the same time, when thread 1 cuts this in half and puts this in his work queue, thread 3 will steal this guy's piece. So thread 0 will create this guy, then thread 1 will steal it from him. Thread 0 will create this piece, thread 2 will steal it from him. Thread 1 will create this piece, and thread 3 will steal it from him. And now all 4 threads have work to do. So the process starts with work stealing. Now, it usually starts with work stealing and then sometimes ends with some more work stealing. If one of these threads gets down to the bottom of his tree really quickly and has no more work to do and has nothing in his work queue, he might start going stealing something from other people's work queues. You always start off with work stealing, and sometimes you end with work stealing. In the middle, there's usually not going to be any work stealing. Okay, so now we see how this would work with 4 threads. It's still going to start with one thread gets the whole job, cuts into 2 pieces, puts this guy in his work queue, but then some other thread immediately steals it from them. When that thread that stole this one cuts it into 2 and works on this one, and he puts this in his work queue, somebody else is going to steal it from his. Until everybody's stolen something from somebody else's work queue, once everybody's got work in their work queue. Now remember, you put things in, you steal from the back of a work queue. So the idea is that when you steal from this guy's work queue, you always want to steal the biggest job in his work queue. So you're always going to, you put new jobs on the right end of the work queue, you steal big jobs from the left end of the work queue. You put little jobs, new little jobs, get put on the right end of the work queue. That leaves the big jobs on the left end of the work queue. You always steal from the left end, the big end of a work queue. That way, when you steal a big job, that means you don't have to steal again for a while. Okay. All right. So right now, here we did the forking. We created and this is version 3 of this stuff. In version 3, we create a thread for every one of these. Every one of these is a thread, but that's going to create thousands of threads. And the process just chokes on it. It's actually not parallelism, it's just stupid. But that pattern, that code, some really smart person looked at that code and said, we can make that code work and turn it into this. I purposely lined this code up so that if you compare them side by side, you can actually see how, as much as possible, they really are almost entirely the same thing. In fact, if it wasn't for this try-catch clause, I could probably even, if I want, I could probably inline that. If you kind of inline the try-catch clause, because it's all just kind of boilerplate. let's see. Let's see how you can actually get them to okay. Other than notice that there's really see how they match up. They match up in a yeah. The pattern of the lines of code are exactly the same. I mean, there's a little boilerplate difference. You need a try-catch clause here. You call start here. You call fork here. You call run here. You call compute here. But logically, this looks exactly like that. But semantically, they're worlds apart. Well, not worlds apart. Yeah, semantically, somebody figured out how to take this interesting idea and make it workable by setting up a work queue and having the key is just change that one line. You change the meaning of that one line from start a heavyweight thread to put something in a work queue. You know, think of it. Somebody looked at this code and thought, if I change the meaning of that one line, I can make this work. How good of an idea was that? The guy sold his company to Intel. The guy who thought of this, he implemented it himself, wrote it all up. He's a professor at MIT. He's the L in the CLR algorithms textbook. He wrote it up, created something called the Silk library that implemented this and sold it to Intel. And I bet he didn't sell it for much. I bet he didn't sell it cheap either. That one little idea was a company. This is one of the great things about software. A little idea, it's actually not a little idea, it's kind of a profound idea, but you change that one line, you change the meaning of that one line and you got a company. You take this code here and say, well, this doesn't work. It creates 1,000 threads. It's stupid. It doesn't work. Then some guy says, yeah, but if I change the meaning of that one line a little bit, create a work queue, build some boiler code to work around the work queue, I can make that code into this code, and now it works. Okay? And then you got a real idea in computer science. At that point, everybody copied this idea. Once he implemented this idea, Intel bought it from him. Java implemented it in their libraries. C++ implemented it in their libraries. I think a few other languages immediately implemented it in their libraries. Everybody kind of said, that's great. We like this. Okay. So then, change this from a thread to put something in a cookie jar, a task jar. Change it from start a heavyweight thread to put something in a jar for somebody else to get later and then do it. Okay, that turned out to be a brilliant idea. Okay, the rest of the code is also very, very much the same. If you there isn't a whole lot. The rest of the code to set this stuff up. I changed some of the comments. If I deleted the comments, you would see that these things still line up real carefully. So I'm now, create the initial, that's creating this guy up here. So in both cases, you have to create the guy up here, okay? Here, in this one, once you create this guy up here, you just jump into him. That starts the ball rolling, okay? You create this guy here and then you jump into him, not as a thread, just main already is a thread, so you just jump into him. Here you have to say, once you've created this guy, so you create this guy that represents this task, you have to say, now remember, invoke is, again, it's weird terminology. What does invoke really do?
Starts a thread pool on the task that you hand it.
Okay, no, careful. Read it from left to right. Who starts the thread pool?
Common pool.
Yes, this one starts the thread pool. So this guy, so you notice that you have a static method in this class here. That static method builds the thread pool. So you build the thread pool. Then what does this do with the task?
Just take the task and divide it to multiple threads.
It takes that
Multiple tasks.
and does what?
We just take the array and divide into multiple
No,
threads.
no. Okay, you create the thread pool. Okay, remember the thread pool would be, remember we said over here, suppose we had 2 threads. Suppose our thread pool was just 2 threads. Okay, what do you have to do to start this process?
Give the thread pool some work.
No. Remember, the thread pool is, okay, suppose we have 2 threads. The thread pool is 2 threads with each one having a work queue. Each one's got a cookie jar that he reaches into and gets jobs out of. So this guy creates the thread pool, which creates a cookie jar for each one of the threads. They're both empty. What does this do?
Fills the cookie jars.
No. Close, but here's the initial task.
Divide the task into 2 cookie jars, 2 threads.
You want to take this initial task and do what with it?
Hand it to a thread.
Right. You put it in one of the cookie jars. You drop this task into one of the cookie jars. That's what invoke does. It takes that initial task and just, it's insert. See, why didn't they just say insert into a task pool or into a work queue? Invoke puts one task into one work queue. Once there's a task in that work queue, that gets the ball rolling. Okay? So this builds all the work queues. If we got 4 threads, we have 4 work queues. That's built by this. So what he does, he asks the operating system, how many cores are there? And the operating system says 4. So he creates 4 work queues, but they're empty. Okay? If the operating system says there's 2 threads, he creates 2 work queues. Okay? But they're empty. Then you call this method on the work queues, on the pool of work queues, and what that does is it picks one of them, usually thread 0, and puts that task in the task queue of that one thread. So that just, it's essentially the same thing as what fork does. Uh-huh.
Yeah, so if you have like many threads and when it picks up a task from work queue of another thread, won't there be too many context switches?
No, you're only going to have as many threads as there are cores. Oh, and I think here's an important idea. When one of these threads starts one of these jobs, he's never interrupted. You do not interrupt. You don't context switch between these. Well, actually, you do. It's just that there won't be a lot of threads. The whole point of this is to only create 1 thread per core. If there's 1 thread per core, you never would need to context switch. Each thread has got his own core to run on, and that's the big difference between 3 and 4. 3 creates thousands of threads, 1 thread for every one of these tasks. 4 only creates a small number of threads. It creates thousands of tasks, but there's going to be 1 thread per work queue, and there should only be 1 work queue per core. So you have each thread gets a core and gets a work queue. So the idea is that there should be a one-to-one relationship between the threads, the cores, and the work queues. Okay, and that's all set up by this guy here. He sets things up so that for every core, there's a work queue and a thread taking jobs out of that work queue. So there won't be a lot of context switching. Okay, right? So
Thank you, Professor.
okay, so over here, we start things out by creating the initial thread. That's the initial guy here, and we just jump into him. Here, we create the initial task. That's this guy. We create the initial task, and then we say, put that task in somebody's work queue. Once that task is put into somebody's work queue, then that thread grabs that task out of the work queue and starts working. He cuts that task into two. He puts that task in his work queue. He jumps into here. But as soon as he puts that task in his work queue, another thread that's got an empty work queue steals it out of his work queue, and he starts cutting it up. Okay? Right? So you can see how as we go along, the pattern for this code just keeps staying the same. It's kind of beautiful in that the really stupid way of doing things, one thread per task over here, looks exactly like the efficient way of doing things, which is one task. The dumb way of one thread per task looks just like the smart way of tasks but not threads. The tasks are just put in a work queue, and then there are worker threads that pull the tasks out of the work queue. But the code is really, really similar, okay? If I tried a little bit harder, I can make these two programs line up almost exactly line for line, okay? Yeah, I think at this point I'm pretty close to lining up line for line. You can see how you switch between them, and there's every line of this code matches up with the line of this code, and the semantics of every line are real close. The two big differences are that line there versus that line there, and also then the similar thing, this line here versus this line here. Okay, you make those two little changes. Both of these changes are put something in a work queue. That puts the initial item in some thread's work queue. This puts the left half in his own work queue. So this is a thread putting the left half in his own work queue. Okay, that's the big change. Instead of creating threads, you put things in work queues. And the way to really understand this stuff is to read the code in parallel like this. Okay, so and he does a good job in section 3.3. He explains the dumb divide and conquer parallelism. So he calls it divide and conquer parallelism. That's the core idea, except it creates thousands of threads. So it's the right kind of idea, but it's the wrong implementation of the right idea. Okay, so that's this picture here, divide and conquer, but it's creating threads. Then 3.4 says, well, what we really want to do is not create threads. We want to put things in work queues. Now, when you get to this section, whoops, I forgot, what did I do here? I must have clicked on a link. When you get to his description of the work queues, he doesn't draw pictures of the work queues. Notice he draws a nice picture of the, like, this is really crucial. This is how the work is being cut up. You take an array, you cut it up into two subarrays, and you think of that's a task and that's a task. Okay, this is a really good picture. This is a real important way of thinking. Unfortunately, he doesn't really draw the work. You look through this whole section, there's no mention of work queues. There's no picture of work queues. I think he really should have drawn a really good picture of the work queues. Unfortunately, I haven't found anybody who does. To me, thinking of the picture of the work queues is really the crucial idea. Is you have to think of how in this picture up here, every time you cut one of these guys up into two tasks, you put that task at the end of the right end of your work queue, and then you go down into here. Then when you cut this up into two pieces, you put this at the right end of your work queue to the right of that guy. So this smaller job is in the front of this bigger job in the work queue. The bigger jobs at the back of the queue for someone to steal, you want to do the jobs from smaller to bigger. So then this job will be in front of this job in the work queue. Then when he cuts this one, then he jumps into here and he cuts this up into 2 pieces. This one will be in front of this one in the work queue. So this one will be in front of this one, will be in front of that one in the work queue. That's how but you want it. I wish he had a nice picture of that. He doesn't draw pictures of the work queues. That's the one thing that when you're studying this, you have to draw the pictures of the work queues yourself. Okay? Okay. Oh, I keep looking at the wrong clock. I'm sorry. So we gone over, what, about 5 minutes now? I keep looking at the wrong clock. All right, so just keep, read the explanation of fork join. Think hard about the difference between, the key is this one and this one. This one creates thousands of threads. You can watch it run. Notice that we're in the process. See, it's how it's built. It's building threads now. It's working its way down the tree. At some point, it's going to work its way back up the tree. Really bad idea. Do that on your computer at home. See, I'm already up to 30,000 threads. Okay, and now I'm back. I peaked at 30,000 threads. Now I'm starting to decrease. Okay, so now the threads are dropping back down. So the tree built up to a massive number of threads, and now it's shrinking back, and it shrunk down to, oh, it's back to growing again. It must have started growing on the other side. Okay, so just run the code on your machine, watch it in Task Manager, watch how the threads grow and shrink, and then run the fork join one, and you'll see the fork join one doesn't create. The fork join one will be a static number of threads. There won't be a growing number of threads. There'll be a static number of threads. Okay, so we'll go quit there.
I have something to talk about. So I've worked with the fork join program that you gave us, section 3-4A.
Yeah.
I think I know why it doesn't scale well at all.
No, it doesn't. It doesn't scale well on my code, on my program either, on my machine either.
I think it's memory bound.
I don't know.
Because even when I scaled it up to 1 billion integers, gave it larger job sizes, scaling it up to like I think 10 million a piece, I still only got about 1.5 times the speed for fork join. Like,
using how many cores?
How many cores? I have 4 cores, 8 threads.
Okay.
And I also, because even then it was completing the job too fast at 1 billion items, I said, all right, so each job that you do it 10 times.
Yeah, try to keep doing it over and over. Yeah.
And even then, the simple solution took 3.2 seconds and the fork join solution took 1.8. So it pulled ahead. I'm thinking it's just a memory bounding issue.
I don't know. I've not come up with an answer with that. Yeah. This is supposed to be one of the core technologies in modern Java for speeding things up. Yeah, there's another one's called parallel streams. So fork join, parallel streams, those are 2 really common technologies for speeding. And this one, yeah, the performance seems really mediocre. I'm not sure. Maybe it doesn't. Maybe this is about as good as you can get. I have a feeling there's something wrong. I don't think there's anything wrong in this code. The guy who wrote this is pretty famous, and the code looks correct to me.
Did he talk about what kind of scaling you should see?
He wrote this I think he does have some numbers in his, I think he did have some numbers in here. Maybe not. I thought he did. Yeah, read it real carefully. I thought he did have some numbers about scaling. And if my memory is, they're not super impressive. But the same
No.
but at the same time, he wrote this when there was mostly just 4-core machines. Like
I mean, it's
my
still what a
machine has
lot of
got,
people are running with.
pardon me?
That's still what a lot of people are running
Yeah,
with.
but this laptop's a year old and it's got 6 physical cores and 12 logical cores. But I'm not getting any scale. Yeah, I'm getting almost no speed up.
Mm-hmm.
I don't know. I keep hitting this brick wall every time I try to do parallelism. You know, it's really hard to get real speed ups. It's really hard to get real speed ups. There seem to be so many things that can get in your way that you're not aware of that it's really hard to get real speed ups. Yeah, it's a good question. I do not get it. I don't see what the problem is.
Like I said, I think it's a memory bandwidth issue. The RAM just cannot feed data from those
Oh,
arrays
I see what you mean.
fast enough to the cores.
I
Because that's
see what.
all this is doing is it's reading
Ah,
an
so we need
array
a bet.
in memory.
Oh,
It just cannot keep up with the speed of the CPU.
that's a real good point. That might be it. That all you're doing is walking an array as fast as possible. And
Like
possibly
you're doing almost nothing
Yes.
with the
Yes.
data. You're just adding two numbers together.
Right.
CPUs can do
So-
that.
So you're saying that the
instantly.
bound is how fast you can stream through an array, and that doesn't seem to be sped up by 4 cores because they're accessing the same memory.
Yeah, it seems like the system RAM can supply data about twice as fast or a little bit slower than twice as fast
if
than
these things
just one core can handle.
What you really need is what we call NUMA. Remember we talked about NUMA, where you give each CPU its own memory bank. That would possibly speed it up. Because actually these
doubt it.
CPUs are sharing the same memory bank.
So here's what modern boards will do. They will use memory channels. So I have a dual channel machine.
Mm-hmm.
So
That doesn't
2
help with
cores will take 1 channel.
Yeah. Mm-hmm.
And I'm thinking that they are outstripping the
Yes.
amount of bandwidth
That
each
sounds
channel
like-
can provide.
Yeah, that sounds real reasonable to me. That this is actually not a good example to be using. Because
Basically, we need a more expensive operation
Yes.
that can happen purely on the CPU rather than needing to be
Yeah, so-
constantly pulling from system memory.
I'll have to look, because the examples that everyone uses either find the max in an array, sum an array. So they're looking at examples that are just like this one. They're bound by how fast you can access the array. So
Mhm.
yeah, so
Which doesn't really make sense. It's pretty well known in computer science that memory is slow.
Yeah, not modern memory slow, unless you can get things to run out of the cache lines.
Yeah. And I'm thinking we're outstripping that too.
Yes, yeah, because we're just doing nothing but array, stepping through memory with just nothing but So
a simple example that comes to mind that might work better would be the Fibonacci sequence.
no, that's a lousy example. Actually, a lot of people use that one. The trouble, I don't know. I don't like that example.
It doesn't use much memory access.
I know.
Everything that it does can happen in registers.
That's the MIT guy that invented this. That's his go-to example.
Mm-hmm.
He uses the Fibonacci example. So if you look in his
it doesn't
book,
do anything useful.
Yeah, I know.
But it's work.
I don't know. That's his go-to example. He does the Fibonacci. He does the recursive Fibonacci's. That's his go-to example.
I would actually avoid the recursive one, mainly because I think it would use a lot of memory accesses.
Well, but you want it to be fork joined. So you want it to be recursive because you want to build up a lot of tasks. That's the whole point, is to build up lots of tasks. If you do the iterative one, then you don't need fork join. That's why it's a bad example, because you have to do the stupid version of Fibonacci to get an example that fits into fork join. So you have to use a stupid algorithm to get it to work in this framework. So, because you normally would do you should do the Fibonacci using dynamic programming. Yeah, so you should do Fibonacci using dynamic programming. That's super fast. Instead, you do Fibonacci recursively, but then it fits in the fork join. So it's not a good example. Yeah, a good question is what would be a nice test case for this stuff? Because I think you're right. That might be what's really stopping us from getting any speed up, is that we can't access memory any faster than we are.
Text searching seemed to have worked well for me for a project that I did last year. It scaled seemingly exceptionally well.
Yeah, that might be, it might be that we need just like a big database of words and do some kind of word searches and things like that. That
once you deliver the data to the CPU, it chews on it for a while.
Yeah. That might be a good example. Yeah, rather than this is looking like, I think you're right. I think that it's the actual algorithm itself is just failing. It's just too IO memory bound. So that would mean you'd need an algorithm that's really bound to the CPU, not bound to memory. Yeah, maybe something like searching. Yeah, searching might be a good one. Some kind of pattern matching kind of searching. Yeah.
For me, the system scaled with like disk IO.
Okay.
As long as I had cores to feed, it didn't seem like I was going to hit an upper limit.
Okay. Yeah, but the key thing about this example is the code patterns are there. They show you what the code looks like. So from that point of view, it's unsatisfying that we don't get speed ups, but we are looking at the right code. Yeah, we're looking at the right logic to everything. Okay, well, we've gone way over. I don't want to keep you guys from having fun. So, I'm going to try to get the videos up on someplace for you to look at them. And if you have questions, send me an email. And I'm going to, at this point, just end the meeting, okay? Any last question? Okay, all right, thanks. Good night. Bye-bye.
Good night. Bye.
Good night.